Welcome to this explainer. You know, over the past couple of years, generative AI has gotten ridiculously fast, thanks to some truly massive mathematical breakthroughs. If you've been watching the AI space at all, you know that generating high-quality images and audio used to take quite a bit of patience. But recently, the underlying architecture completely shifted. It transformed what used to be a mathematically heavy, computationally expensive stroll into an absolute sprint. Today, we're going to unpack exactly how that happened by looking at the specific math under the hood.
Okay, let's just dive right in with a massive question that completely shifted the entire AI landscape. Seriously, how did the top-tier models suddenly get up to 12 times faster without sacrificing any of the stunning quality of their outputs? It wasn't just a matter of throwing more raw computing power at the problem either. The answer lies entirely in how we teach neural networks to navigate from pure static noise to perfectly formed data.
So here's our roadmap for today. We'll start with the speed problem, then look at the straight line solution, move into rectifying the flow, explore why flow matching won, and finally wrap up with the new AI standard. Let's get right into it.
Starting with Section 1, the speed problem, or what we usually call the diffusion bottleneck.
Now, there is a stark contrast between wandering down a winding, curved path versus hopping on a direct flight. Traditional diffusion, specifically DDPMs, while they rely on heavily curved paths to get from noise to a final image, demanding anywhere from 20 to 50 incredibly careful inference steps. But flow matching? It acts like a direct, straight-line flight, cutting that requirement down to a mere 1 to 4 steps. It is fundamentally a problem of geometry.
To really appreciate this, we got to look back at how early diffusion started out. Those initial DDPM models required a grueling 1,000 steps stochastic walk just to get from pure noise, what we mathematically call N0I, essentially pure static, back to the actual data distribution. Because the mathematical path from that noise to the actual image was so curved, the ordinary differential equation solving the reverse process was incredibly stiff. The model had to take tiny computationally expensive steps to avoid veering completely off course. Even with clever optimization hacks like DDIM, you're still stuck computing dozens of deterministic steps.
Which brings us to Section 2, the straight line solution. Let's flatten that curve.
So how do we straighten out that path? Enter a concept known as the velocity field, denoted as v theta. Think of the velocity field simply as the output of the neural network acting like a compass. Instead of guessing a curved route through the noise, we explicitly train the model to be a compass that points directly toward the final data. It tells the system exactly which direction to move to get from the current noisy state directly to the target image.
And honestly, this is the core genius of flow matching. It defines a straight line interpolation from what we call x1, which represents pure noise, directly to x0, the actual clear data. If you can mathematically define this straight line, your target derivative is constant. That means a single Euler step from time 1 down to time 0 is theoretically all you need to generate an image. You just integrate the learned vector field backwards in time. It is beautifully simple on paper, literally taking one giant leap instead of 1,000 baby steps.
But there's the catch, leading us to Section 3, rectifying the flow, where we straighten those paths out. Because here's the thing, our straight lines aren't always perfectly straight on the first try. Theory and practice sometimes need a bridge to connect them, right? This brilliantly illustrates Liu's reflow procedure, also known as rectified flow. The issue was that straight-line flows learned by the model often curved slightly because multiple different starting points could accidentally map to the same noise. To fix this, you iteratively straighten the learned paths. First, you train a flow model on random pairs. Second, you sample new pairs by integrating that first model from noise to its landing data. And third, you train a completely new model on these newly paired examples. Because these pairs are now ODD matched, the line between them is genuinely, mathematically flatter.
And you want to know the magic number for this straightening process? It's exactly 2. In practice, it only takes 2 iterations of this reflow process to achieve the exact same quality that used to take 50 steps in traditional diffusion, all in just 2 simple inference steps.
Moving right along to Section 4, why flow matching won, and the massive industry shift it caused.
Look, this wasn't just some niche academic experiment. It triggered a total industry overhaul. The adoption was practically overnight, and for 3 main reasons. First, developers loved it because it offers simulation-free training. You never have to unroll the ODE during the training process, making it super trivial to implement.
Second, it provides much better loss geometry. Because the paths are straight, you maintain a consistent signal-to-noise ratio, completely avoiding those nasty noise schedule issues you'd see at the edges of traditional diffusion. And third, the inference speed is just incredibly fast. When combined with consistency distillation, you can literally get it down to a one-step sampler. No way around it, it's a game changer.
Actually, a quick heads up for the developers out there studying this. Do not get tripped up by the time parameterization. Flow matching sets time t from 0 at the data to 1 at the noise. Traditional DDPM uses time t from 0 at the data all the way out to a capital T at the noise. They move in the exact same direction, but on completely different scales. Research papers constantly mix up these scales, which can lead to major headaches when you're coding this from scratch.
Which brings us to our final stop, Section 5, the new AI standard and the 2026 stack. So what does this straight-line math actually look like in the real world today? When you look at the production stack for the near future, it is absolutely dominated by this exact architecture. For best quality text-to-image, you have models like Stable Diffusion 3 and Flux.1. For audio generation, there's AudioCraft 2. From generating high-definition video in models like Sora, all the way to predicting complex particle and molecule trajectories in physics, flow matching is the undisputed engine under the hood.
If you really want to see the real-world impact of this, just look at this massive drop in latency running on an L4 GPU. The raw Flux.1 model takes about 15 seconds to generate an image using 50 steps, but the distilled version, Flux.1 Schnell, it compresses that 15-second generation down into a blistering 1.2 seconds using only 4 steps. It achieves this breathtaking speed precisely by using these rectified straightened paths.
So the crucial takeaway from this whole explainer is the new production rule of the industry. Pure diffusion is, for all intents and purposes, legacy tech. If a paper claims to be faster than diffusion, they are almost certainly using a flow-matched-based model combined with distillation. This combo is the ultimate production standard for fast generation going forward. We've seen it conquer text-to-image, text-to-video, and complex audio by simply flattening the mathematical curve. It leaves you wondering exactly which industry this incredibly efficient math will disrupt tomorrow. Will it be real-time virtual reality generation, or perhaps folding proteins even faster in the medical field? That's the sheer power of finding the straightest line from noise to reality. Thanks for joining me for this explainer, and keep your eyes on those straight lines.